There are clocks in the sky so steady that a change of a millionth of a second can betray the tug of a black hole halfway across the galaxy. And those clocks aren't gears or crystals or electronics. They're dead stars that still refuse to be quiet. Picture a city, compact and bright at night, shrunk down until it could fit inside a small county. Now shrink it again until it could sit under a blanket the size of a metropolitan area. Keep shrinking until the whole city is only about 20 kilometers wide. That's a pulsar. It's the leftover heart of a massive star after the star explodes. The outside gets blown into space in a supernova. The core collapses into a neutron star. It keeps almost the sun's mass but squeezes it into that tiny sphere. Gravity at the surface is outrageously strong. Density is beyond imagination. A teaspoon of that matter would weigh as much as a mountain. If you stood on the surface, which you can't, a jump would not carry you even the thickness of a human hair before you fell back with the force to crush atoms. The crust is so stiff that a mountain on this world might be only a millimeter high. A single ridgeline the height of a grain of sand could hold more weight than a mountain chain on Earth. A pulsar is a neutron star that spins and beams. The spin comes from the parent star. When a huge star collapses, it spins faster, the same way a figure skater spins faster when drawing in their arms. The magnetic field also gets squeezed and strengthened until it becomes intense beyond ordinary language. The pulsar's magnetic poles are not lined up with its spin axis. That misalignment is the trick. Charged particles near the magnetic poles get accelerated to near light speed and release beams of radiation that sweep around like lighthouse beams. If one of those beams sweeps across Earth, we detect a pulse. Most of those pulses are in radio waves. Some pulsars flash in X-rays or gamma rays. A few, like the famous one in the Crab Nebula, even flicker in visible light, though you'd need a good telescope to catch it. The result is a cosmic lighthouse that ticks with a regular beat, from rotation rates of a few seconds down to a few thousandths of a second. The fastest, called millisecond pulsars, spin hundreds of times every second. Imagine a city-sized object turning over and over, again and again, faster than a kitchen blender. Those pulses feel like the clean beat of a metronome. They're not sound. They're radio waves arriving on time, like a drummer who never tires. When that metronome changes, even slightly, the cause matters. The pulsar is losing a little energy each second. It's converting spin into wind and radiation. Over long times, the rotation slows. Astronomers call that spin down. But the star does not slow smoothly. Sometimes a pulsar stutters and changes speed in a sudden jump. That jump is a glitch. The crust can crack and shift like a starquake. Below that crust, the interior is so dense that neutrons flow like a superfluid, which is a quantum state with zero friction. The superfluid can rotate in ghostly patterns that store angular momentum, and then transfer it to the crust in a snap. The whole star jerks a tiny bit faster. We catch the change in arrival times of the pulses. It's the only way to read the drama unfolding inside a sphere of matter we cannot visit. Before the word pulsar existed, a young researcher noticed a signal that nobody expected. In 1967, Jocelyn Bell Burnell was surveying the radio sky with a new array built with her supervisor, Anthony Hewish, and others. She was tracking miles of paper chart, learning to spot the usual noise and bursts. And there, amid the scruff, she found a tiny regular tick. It was too precise to be lightning, too steady to be a known source. The team jokingly labeled it LGM1 for Little Green Men 1, because the pulses were so exact that a transmitter seemed possible. But there were no aliens. There was a new class of star. More sources turned up in different places with different periods. The discovery cracked open a door in astronomy. Something in the universe, small and heavy and fast, was broadcasting with the accuracy of a lab clock. The lighthouse model emerged from theory and observation. The magnetic axis tips away from the spin axis. The magnetic field traps a cloud of charged particles, making a magnetosphere. Near the magnetic poles, where field lines open into space, particles accelerate along the lines and emit radiation. Because the star rotates, the beams sweep. When the beam crosses our telescopes, we see a pulse. The shape of the pulse depends on the fan shape of the beam and our line of sight. Some pulsars show a main pulse and a secondary one from the opposite magnetic pole. Others show complicated shapes because the emission region is not a thin pencil but a swath, more like a fan or a hollow cone. The magnetosphere is not simple, either. Currents flow. Particles stream outward. A wind carries energy away. The entire structure lives in the tension between the star's rotation and its magnetic grip on charged matter. Even those regular beats race through a medium that can slow and smear them. Space is not empty. Between stars, a very thin gas floats, and most of its atoms are ionized into electrons and protons. Radio waves do not all travel through that plasma at the same speed. Lower radio frequencies lag by a little, the way deep notes might be muffled in a fog, while higher ones arrive earlier. Astronomers call the effect dispersion. They measure how much the lower frequencies are delayed compared to the higher ones and compute a number called the dispersion measure. It tells how many free electrons are along the path, like timing how long a flashlight beam takes to cut through fog of known thickness. With many pulsars spread across the sky, we can build a map of the interstellar medium. Different lines of sight cut different layers of electron fog. The map helps correct the timing and also tells us where the gas is denser, where supernovae have carved bubbles, and where magnetic fields sculpt the plasma like wind shapes snowdrifts. Precision is the key. Millisecond pulsars are the champions. Many of them live in binaries. Long ago, they were ordinary pulsars that had slowed down. Then they had a second act. A companion star swelled and spilled gas onto the neutron star. The infalling matter carried angular momentum. It spun the star back up, the way a stream might spin a water wheel faster. This spin-up is why they're called recycled pulsars. The accretion cleared. The companion became a small star or even a faint amber, and the neutron star now ticked at astonishing speed with mechanical grace. These clocks are so stable that we can predict the arrival of a pulse to a few hundred nanoseconds. Over years, that adds up to a measure of stability rivaling atomic clocks on Earth. With that precision, we test gravity in extreme places. Consider a binary pulsar discovered in the 1970s, where the pulsar and its companion, a dense star, orbit each other in hours. As they whirl, they lose a tiny bit of orbital energy by radiating gravitational waves. The orbit shrinks. Over years, the periastron time shifts. The amount of shrinkage matched what general relativity predicted. Later, a double pulsar system was found where both stars are pulsars. There the tests became even sharper. You can time both stars and watch their dance with a detail that makes textbook examples feel dull. The orbits precess. Signals delay as they pass through curved spacetime near the companion. Every term in the equations gets a chance to stand up and be measured. The results have been a steady vote of confidence for Einstein's theory. But the laboratory is a pair of city-sized objects moving at a few hundred kilometers per second in gravity billions of times stronger than Earth's. It's the best stress test of gravity we have beyond black hole mergers. Pulsars let us do a stranger trick. We can use them as a galaxy-wide gravitational wave detector. Millisecond pulsars scattered across the sky form a timing array. Each one sends a steady beat. If a very slow gravitational wave passes between us and them, space itself stretches and squeezes. The path shrinks a little, then grows. The rhythm of the pulses shifts by a hair. The effect is tiny, but it has a signature. Nearby pulsars shift in related ways. Pulsars on opposite sides of the sky shift in patterns that match the geometry of a wave sweeping across the galaxy. The waves we're sensitive to in this way are incredibly slow. Their frequency is in nanohertz. That means the waves rise and fall over years. Imagine 100 metronomes spread across a football field, all in time. The field is covered in a rubber sheet. If a slow swell rolls across the sheet, the distances between the metronomes change a little. Their ticks arrive just slightly earlier or later at your ears on the sideline. If you record those ticks for years, you can prove the swell is real. That is how a pulsar timing array hears the very slow dance of supermassive black holes in distant galaxies as they orbit and spiral together. Pulsars also become tools for travel. Every pulsar has a known position on the sky and a characteristic timing signature. If a spacecraft can detect a set of pulsars and measure the arrival times of their pulses, it can triangulate its position much like GPS. You don't need satellites around Earth. You can use beacons that live all over the galaxy. X-ray pulsars are especially helpful because X-ray detectors can be compact and the pulses are sharp. The spacecraft reads the sky's clocks and knows how far it has drifted. It is navigation by lighthouse in interstellar form. To understand why these stars spin down at all, we return to the magnetosphere. The rotating magnetic field drags charged particles. That drag launches a magnetized wind that carries energy away. The star pays for that wind with its spin. Over time, the period grows longer. The rate of change tells us how strong the magnetic field is and how old the pulsar might be in a rough sense. Yet there are surprises. The youngest pulsars, like the one in the Crab Nebula, spin quickly and have energetic winds that light up the supernova debris with a ghostly glow. Middle-aged pulsars slow and beam steadily. Old pulsars grow quiet. Some are revived by accretion and become millisecond pulsars. Some return to quiet again. A few exhibit strange moods. They switch between bright and dim states. They wander in phase. They sometimes shut off, then return days later, the way a candle might flicker in a room where a window opens and closes. Glitches tell us about the interior. The crust is a rigid lattice of nuclei packed together. Under the crust lies a sea of neutrons, superfluid and superconducting. Superfluid rotation is not like the flow of water. It carries quantized whirlpools. Those vortices can pin to the crust, storing rotational energy. When many of them unpin at once, the superfluid dumps a bit of its stored spin into the crust. The star's outer layer speeds up slightly. We notice because our clock suddenly runs a bit fast. Later, the star relaxes back to its long-term slow trend. The details are hard to model because the superfluid lives beyond our everyday intuition, but every glitch is a hint. Each one is a postcard from a place where matter is pushed to limits we cannot reach in a lab. The family of neutron stars has flavors. Not every neutron star is a pulsar. Some are radio quiet. Some shine in X-rays because they're hot. Some have magnetic fields 1,000 times stronger than typical pulsars. Those are magnetars. A magnetar's magnetic field can twist its crust and create giant flares of X-rays and gamma rays. Magnetars can pulse, but their beaming and timing can be messy. They are cousins, not twins, to ordinary pulsars. In contrast, millisecond pulsars are the spun-up elders, thin and fast and stable. Many millisecond pulsars live with companions in tight systems. Some are called black widows or redbacks because their wind erodes the companion star, stripping gas like a sandblaster. Others are in star clusters, where crowded neighborhoods make binary interactions common. Double pulsar systems, where both stars are pulsars, are rare gems. They give us a chance to time two lighthouses circling each other and see each beam cut through the other's magnetosphere. Records live inside this family tree. The fastest pulsars spin about 700 times per second. The heaviest neutron stars weigh close to twice the mass of the Sun. Those numbers matter. A star that heavy tells us that the matter inside must be stiff enough to resist collapse. It constrains the physics of dense nuclear matter. At the light end, there are pulsars whose beams can be seen with modest telescopes, like the CRA, which flashes dozens of times per second and can sometimes be caught with sensitive cameras. The Vela pulsar, a middle-aged star, glitches often, and each glitch is a lesson. There are pulsars with planets, too. Long before exoplanets were found around Sun-like stars, a pulsar was caught with a small system of rocky worlds. Those planets likely formed from debris after the supernova, a quiet arrangement circling a dead engine. Human work with pulsars is a choreography of patience. A radio telescope listens for hours, and then for days, and then for years. The pulses are averaged to build a stable profile. The arrival times are compared with a model that predicts how the Earth's motion, the pulsars spin, and any orbital motion will affect timing. You correct for dispersion. You correct for the rotation and wobble of Earth. You correct for the little drifts of observatory clocks. What's left should be pure pulsar. Then you search the leftovers for physics. Is the period changing as expected? Is there an extra delay because the beam passes near its companion and feels the warping of spacetime? Is there a wobble because a planet tugs on the star? Is there a long, faint wander common to many pulsars that hints at those slow gravitational waves? The discovery story still reads like a fable. Jocelyn Bell Burnell did not stumble over a headline. She trained her eyes, trained her mind, and earned that find by paying attention to what was different. The signal was nicknamed LGM1 for a few days because it tickled that part of us that wants contact. It survived because it demanded a better explanation, and the better explanation opened a new field. That is a useful pattern in science. Pay attention. Trust your curiosity. Reject the easy answer when the new one is better. There are misunderstandings that cling to pulsars, so let's sweep them away. Pulsars are not sending messages. Their pulses are natural, the byproduct of rotation and magnetism and plasma. We do not hear them as sound. We translate radio waves to audio for our own ears sometimes, but the sky is not literally knocking. Not every neutron star will ever be a pulsar for us. The beams are narrow, Think of a flashlight on a dark beach. If the beam never sweeps across your spot in the sand, you will never see it, even if the lighthouse is healthy. Some pulsars are loud in radio. Some are bright in X-rays. A few touch the visible band. That spread is normal because the emission depends on how particles are accelerated and where in the magnetosphere they are. Radiation forms. The lighthouse is real, but it is complex and lies inside a magnetized storm. If you hold a pulsar in your thoughts, hold two images at once. First, the violence. A star many times heavier than the sun burns all it can, then crushes itself when its core runs out of nuclear fuel. The outer layers fly outward at thousands of kilometers per second, lighting a nebula that glows for centuries. The core collapses, but not to a black hole. Neutrons pack so tightly that quantum rules, not everyday pressure, hold them up. The magnetic field tightens, the rotation skyrockets, and the newborn neutron star cries in radio and X-ray and gamma ray. Second, the order that follows. The pulses settle. The beat stabilizes. That death, in slowing down, becomes one of the most reliable rhythms in the universe. Out of violence comes a clock. Inside that clock is physics we still don't fully master. How stiff is neutron star matter? Do exotic particles, like hyperons, appear at high density? Does the center host quark matter, a soup where protons and neutrons melt into their ingredients? What shapes does matter prefer at the base of the crust, where theory predicts strange pasta phases of nuclei, with shapes like spaghetti or lasagna? Each precise mass we measure, each radius we infer from X-ray light curves, squeezes the possibilities. A glitch shifts the constraints again. A starquake hints at how brittle the crust can be before it snaps. Observations keep getting better because our instruments keep getting wiser. New surveys scan the sky wide and deep, catching thousands of pulsars in places we once could not see. Low-frequency arrays listen for slow pulses that hide in thick dispersion. High-frequency dishes cut through turbulent clouds. Space telescopes catch X-ray beams from hot polar caps. Timing campaigns align across continents so there is always an ear open. The timing arrays stretch their baselines from 5 years to 10 to 20. That change makes them sensitive to slower and slower waves. If there is a background hum from many supermassive black hole pairs, it should stand out when enough data pile up in careful stacks. The interstellar medium, once a blur in the background, becomes detailed in these studies. Dispersion tells us the total number of freed electrons along the path, but not their exact distribution. Scattering adds another layer, like looking at a candle through frosted glass and seeing its light smear into a tail. That smearing encodes how clumpy the plasma is. With many pulsars spread across different directions and distances, we can reconstruct a three-dimensional weather map of this plasma. It isn't static. Supernova blow bubbles. Stellar winds push and warp magnetic field lines. Streams of gas flow from the galactic center outward. Watching a pulsar over years lets us watch the fog shift. In the same way that a lighthouse defines a coastline for sailors, pulsar timing defines spacetime for astronomers and navigators. A spacecraft that reads pulsars can know where it is without asking Earth. It listens to the clocks and computes its position from the differences in arrival times, just as a phone does with GPS but on a grander scale and with natural beacons. On the International Space Station, a demonstration proved the idea in principle with X-ray pulsars. Far from Earth, A craft on a journey to the outer planets or beyond could keep its bearings without waiting for a radio round trip to a dish back home. The sky itself would be its reference frame. Stories of extremes are irresistible here. Consider a newly born pulsar that spins dozens of times per second. Its magnetic field hurls particles outward in a wind that can sculpt the supernova remnant into rings and jets. In its youth, the star's spin down power can rival the brightness of 100,000 suns, but most of that energy is not light you can see with your eyes. It's in particles and magnetic fields. As the star ages, it slows. In a few million years, the beam can grow too weak to detect. Then millisecond pulsars write a different ending. They may be billions of years old, yet they spin hundreds of times per second and can stay steady for ages because their beaming is efficient and their spin is maintained by the spin up they received long ago. Magnetars teach another extreme. Their fields can rearrange themselves catastrophically. When the field cracks the crust, or when twisted field lines reconnect, the star can flash in high-energy light. These flares travel half a galaxy and still tick detectors on Earth. Magnetars have been linked to some fast radio bursts, those surprising radio flashes that last milliseconds and then vanish. Not all fast radio bursts come from magnetars, and not all magnetars burst this way, but the family resemblance is strong. Again, neutron stars provide the lab. Gravity, magnetism, and quantum matter meet in a compact ball and produce phenomena that stretch our models. There is also art in pulse profiles. When you fold a pulsar's signal on itself to line up the pulses and average them, you get a stable shape. It might have a sharp leading edge and a slow decay. It might have two peaks with a dip between. It might change gradually over months as the pulsar precesses, which means the spin axis wobbles like a top. That precession can be caused by torques from the companion in a binary, or by the fact that a spinning neutron star does not have a perfectly symmetric shape. The way profiles change tells you about the geometry of the beam and the height above the surface where the radiation flow, RMS. You never see the machine directly. You only see the heartbeat in silhouette and learn to read shape as a map. Because pulsars are so regular, they lay traps for sloppy thinking. A sudden change in timing could be a glitch. It could also be a new planet. It could be the effect of interstellar weather changing the dispersion slightly. It could be the clock at the observatory drifting. It could be Earth's plate under the dish swelling with temperature. Good work is careful work. Teams coordinate. They compare data from different telescopes. They watch how the timing residuals, the leftover differences between model and data, correlate from one pulsar to another. That is how timing arrays rule out local problems and gain confidence that a common wave is real. Think again of scale. The star is 20 kilometers wide. The magnetic field lines stretch for thousands of kilometers. The radio beam can form hundreds or thousands of kilometers above the surface. The orbit in a binary can be a few million kilometers across, with periods of hours or days. The gravitational waves we hope to catch have wavelengths measured in light years. The whole galaxy becomes part of the instrument. We are timing quick ticks to understand slow swells. It's like using the flicker of a candle to measure the rise and fall of a tide. Because these stars are so dense, the physics of their structure is a frontier. Laboratory experiments can squeeze matter in collisions or in diamond anvils, but not to these pressures for long times. So neutron stars become our experiments. We measure mass with high precision using timing in binaries. We infer radius from how the star's surface emits X-rays as it rotates, or how it cools after an outburst. We watch how quickly some stars cool over decades and infer whether neutrinos, those ghostly particles, carry energy away efficiently from the core. Each study pries a bit of information from a place sealed by gravity. There is wonder in the idea that something so deadly is also so helpful. A supernova can sterilize a region of space. A magnetar flare would ruin any nearby planet's day. Yet the leftovers are steady, patient, and generous. They time our instruments. They map our fog. They verify our theories. They whisper about waves that are otherwise too large and slow to feel. They offer a way to steer a path in deep space. You can imagine the lives of these stars as arcs. A massive star burns hot and fast. It dies young in cosmic terms after a few million years. Its core, squeezed and spun, becomes a neutron star. It might flash like the crab. It might drift toward quiet. It might find a partner, steal mass, and race again as a millisecond pulsar. It might live in a cluster and suffer encounters that swap its companions. It might end in a double neutron star system and, over vast time, spiral into a merger that lights the sky in gravitational waves and heavy elements. Gold in a wedding ring could trace its ancestry to such a collision. In that sense, even the quiet tick of a pulsar connects to the heavy atoms in your hand. Frontiers call from every side. New telescopes on the ground are tuned to find faint, fast pulsars that have hidden in noisy parts of the sky. Space missions that can catch X-ray pulsations with high precision will refine radii and masses and test theories of matter. Timing arrays with more pulsars will take the first detections of a background of gravitational waves and turn them into astronomy, where individual sources might be identified, where the hum becomes a choir. Theories of magnetospheres sharpen as computers learn to simulate plasmas with more realism. The crust's nuclear pasta moves from a lovely phrase to a set of numbers that can be compared with glitches. Even the mythic silence of empty space gets pierced, as we learn that the interstellar medium is a living, shifting thing that can be measured and predicted. It's also worth remembering how often we've been fooled by what we expected to see. Pulsars were once mistaken, for a few very human days, for aliens. They aren't. But if one day a signal does arrive with content we can't dismiss, our ability to separate the natural from the artificial will depend on all this groundwork. Knowing what neutron stars do helps us keep our heads when the sky throws a surprise. It's not an argument against wonder. It's a way to keep wonder honest. The image that started all this was simple. A beam sweeping, a tick repeating. The image that holds it together is richer. A city-sized star, 20 kilometers across, spinning hundreds of times per second, with the gravity to flatten mountains into ridges the height of a thumbnail, and the steadiness to mark time better than anything else in nature. Its beam crosses us. We catch the beat. We subtract Earth's motions and the interstellar fog and the quirks of our machines. What remains is the star's heartbeat and the shape of the space between us and it. Hold that in your mind at the end. You, on a planet circling an ordinary star in a crowded arm of a barred spiral galaxy, are listening to a lighthouse that is also a clock. Its face is not a dial. Its hands are not metal. Its ticking is not sound. It is timing written in radiation, a drum you can only hear if you build the right ears. The beam sweeps. The pulse lands. And somewhere far away, a slow swell passes across the galaxy, stretching the silence by a breath. then letting it relax, while the little clock on the far shore keeps perfect time. A dead star can keep time better than an atomic clock, and the faintest change in its beat can reveal a giant black hole stirring space from 1 billion trillion kilometers away. That is the power of a pulsar, a city-sized star that refuses to stop telling the truth. Start with the picture. Take something with the mass of our sun and crush it into a sphere about 20 kilometers across. That is smaller than many cities. The gravity on its surface is so intense that a teaspoon of its matter would weigh as much as a mountain on Earth. Its crust is stronger than steel by absurd factors. A mountain on this world might rise only a millimeter before gravity presses it flat. This object is called a neutron star because its matter is packed into neutrons, the neutral partners of protons inside atomic nuclei. A pulsar is a neutron star that rotates and shines in beams like a lighthouse. We do not see a constant glow. We see a tick, a flash, a regular sweep caused by the star's magnetic poles failing to line up with the spin axis. Every spin swings the beam past our planet. If the beam crosses our line of sight, we get a pulse. How does such a star come to be? Begin with a massive star, many times heavier than the sun. It burns its fuel fast and furious. When the core runs out of the elements that can support it, gravity wins. The core collapses in a shout of physics. The outer layers rush inward and then rebound. A shock wave blasts them into space as a supernova. The core is squeezed until protons and electrons merge into neutrons. The magnetic field, once spread across a bloated star, is cranked tighter and stronger. The rotation speeds up because the shrinking core conserves angular momentum, the same way a spinning skater speeds up by pulling in their arms. In a blink, a new object is born. It is hot. It is dense. It is threaded by a magnetic field so strong that ordinary words start to wobble. If the magnetic axis is misaligned with the spin axis, and if charged particles are accelerated near the magnetic poles, radiation will pour out along those poles in narrow fans. The star turns. The fans sweep. A lighthouse is lit. Most pulsars announce themselves in radio waves. A few pulse in X-rays and gamma rays. Rare ones flicker faintly in visible light. The rotation can be slow and stately, one turn every few seconds, or shockingly fast, with hundreds of spins each second. Those speed demons are called millisecond pulsars. Imagine a sphere the size of a city rotating hundreds of times per second and not flying apart. Gravity and the stiffness of nuclear matter hold it together. The pulses are so regular that for many purposes the star behaves like a natural metronome. The beat can be predicted years in advance, down to fractions of a millionth of a second. When that beat deviates, something real has happened out there. To hear a pulsar, a radio telescope collects the faint whispers from space and converts them to electric signals. The pulses do not all arrive equally. Space between stars is filled with a thin fog of ionized gas called plasma. Radio waves traveling through this plasma behave a bit like light shining through fog. Lower frequencies, the deeper notes, get delayed more than higher ones. Astronomers call this dispersion. The amount of delay tells us how many electrons lie along the path from the pulsar to us. That count is called the dispersion measure. Think of shining a flashlight through fog toward a distant wall and timing how the color spreads out. By measuring the spread, you learn how thick the fog is along that path. With many pulsars spread around the sky, we can build a map of our galaxy's fog. the interstellar medium, and watch it shift with time. The story of discovery is human and sharp. In 1967, a graduate student named Jocelyn Bell, later Jocelyn Bell Burnell, was monitoring a new radio array built with her supervisor, Anthony Hewish, and others. The array used miles of wire and acres of land. The signals were recorded on paper charts that spilled out feet at a time. Bell learned the quirks of the sky and the instrument. She noticed a bit of scruff that repeated with uncanny regularity. It ticked like a metronome. It returned night after night with the sidereal sky. It was not lightning. It was not a known radio source. For a moment, the team considered a joke label, LGM1, short for Little Green Men 1, because the regularity was so startling. Soon more sources with different periods appeared. The joke died. A new class of object had been found. The pulsar was named, and astronomy suddenly had clocks scattered across the galaxy. Why does a pulsar slow down? Energy must go somewhere. The spinning star, wrapped in its magnetic field, drags charged particles around. That drag launches a magnetized wind. The wind carries energy away. The beam itself carries energy away. Over time, the star pays for this loss by spinning more slowly. Astronomers track this spin down. The rate tells us about the magnetic field and the star's environment. Yet the slowing is not always smooth. Sometimes a pulsar's rotation jumps suddenly. This jump is called a glitch. The simplest picture is a quake. The crust, thin compared to the whole star but incredibly strong, can crack and shift. Inside the crust lies a superfluid, a quantum liquid of neutrons that flows without friction. It can store angular momentum in tiny whirlpools. When many whirlpools untin from the crust at once, they hand their stored spin back to the crust. The star's surface layers speed up a little. We see the pulses arrive slightly early. Then the star relaxes back toward its long trend of slowing. Each glitch is a probe of an interior we cannot touch. It is a natural experiment in matter at densities beyond any laboratory. The lighthouse model needs a little filling in. The magnetic field lines near the poles open into space. Along those open lines, particles accelerate to near light speed. When charged particles bend, they radiate. In a pulsar magnetosphere, the dominant radiation in radio is called coherent emission, because the particles act together. Higher up in energy, X-rays and gamma rays come from different processes in the outer magnetosphere or near the surface. The geometry matters. If the beam is like a hollow cone, our line of sight may cut across it once per rotation or twice, giving a second pulse. Some pulsars show complex pulse shapes that change over months or years. That can happen if the star's spin axis wobbles, a motion called precession, or if the magnetospheric currents reorganize. We infer structure from shape. We never see the engine directly. We read its shadow in time. Now let's talk flavors. Normal pulsars are born spinning relatively fast and slow down over millions of years. Many become too faint to detect in radio, even though the star persists. Millisecond pulsars are different. They were slowed long ago, then revived. In a binary system, a companion star can puff up and spill gas onto the neutron star. The falling gas carries angular momentum. It spins the neutron star back up, the way a stream spins a water wheel. This is recycling. When the accretion stops, the neutron star is now a light, stable spinner. Many millisecond pulsars sit in tight binaries with small companions. Some of these systems are called black widows or redbacks. The pulsar wind erodes the companion, stripping away gas. In dense star clusters, where encounters are common, millisecond pulsars flourish because binaries are created and exchanged like dance partners. These spun-up clocks are so stable that they rival the best timepieces on Earth. Cousins of pulsars are magnetars. A magnetar is a neutron star with a magnetic field 1,000 times stronger than a typical pulsar. The field can twist and crack the crust, releasing giant flares of high-energy light. Magnetars can pulse, but their timing is often messy. They are not generally the precise clocks that millisecond pulsars are. They teach different lessons. They show how fantastically strong magnetic fields behave when coupled to dense matter. Some fast radio bursts, those mysterious millisecond flashes from deep space, have been linked to magnetars. Not all fast radio bursts come from magnetars, but at least some do. Neutron stars give us many laboratories at once. Pulsars in binary systems unlock deep tests of gravity. Consider a pulsar orbiting another dense star in hours. We time each pulse and calculate the orbit. General relativity predicts that the system will radiate gravitational waves and lose orbital energy. The orbit will shrink. The periastron, the point of closest approach, will shift over time. The pulses give us a ledger you can audit. Over years, the numbers add up and match the theory. Even sharper is a system where both stars are pulsars. Then you can time two clocks in the same dance. You watch signals delay as they cross the curved space near the companion. You watch the precession of the orbit. You watch everything a textbook predicts in a regime of gravity far stronger than Earth's weak field. These measurements, repeated, refined, and checked, stand as some of the best proofs that general relativity survives in harsh conditions. The same precision opens a path to an even grander detector. If you spread a set of millisecond pulsars across the sky and time them for years, you create a pulsar timing array. Gravitational waves with very long wavelengths, taking years to crest and trough, will stretch and squeeze space along different directions. When a wave passes between us and a pulsar, the distance changes by a tiny amount. The pulses arrive a little early, then a little late. The pattern across many pulsars carries a signature. Pulsars close together on the sky respond in related ways. Pulsars across the sky respond with a different relationship. You can think of 100 metronomes placed on a rubber field. You stand at the edge and listen for years. A slow swell rolls through the field. Some metronomes end up a hair closer to you, others a hair farther, in a pattern that fits the curve of the swell. That is the signal. With enough patience, you can detect the combined hum of many pairs of supermassive black holes orbiting each other in distant galaxies. A chorus emerges from ticks. Navigation becomes a natural extension. Each pulsar is a beacon with a known position and a unique beat. A spacecraft with a sensitive radio or X-ray detector can listen, measure the difference between expected and actual arrival times, and solve for its position in space. It is like GPS, but the satellites are neutron stars scattered across the galaxy. X-ray pulsars are attractive beacons because X-ray instruments can be compact and the pulses are crisp. A demonstration on the International Space Station proved the concept. A deep space probe could one day fly with a star map built from pulsars and guide itself far from Earth without waiting for ground instructions. The sky itself would be the clock and the map. Pulse profiles are a quiet art. If you align many pulses and average them, random noise cancels and a stable shape appears. That shape often has a sharp leading edge and a slower tail. Some profiles show two peaks that mark our line of sight cutting through a cone. Some drift. Some change abruptly when the magnetosphere switches modes. Those switches tell us that the plasma surrounding the star is not passive. Currents can change. Particle acceleration zones can turn on and off. The beam is not a single flashlight bulb. It is a structured fan shaped by electricity and magnetism in an extreme engine. Records matter because they strain theory. The fastest known pulsars spin nearly 700 times per second. They challenge our understanding of how fast a neutron star can spin before it would shed mass at the equator. The most massive neutron stars weigh around twice the mass of the Sun. That pushes our models of neutron-rich matter because not every theoretical recipe for dense matter can support such weight without collapsing into a black hole. Each precise mass measurement trims the family tree of ideas. Radii inferred from X-ray timing and modeling add more pressure to theory. The inner crust may be filled with nuclear pasta, structures that minimize energy by forming sheets and rods. The core might hide exotic particles or even a phase where quarks roam freely. We cannot set up these experiments on Earth. Neutron stars have done the work for us. We simply read the results written in timing and light. Let's return to the everyday stories that make the scale feel real. A sugar cube of neutron star matter weighs more than a mountain. You could line up the whole Himalaya range, and that sugar cube would still have the edge. A ridge only a millimeter high on the surface of a neutron star would count as a mountain. A sphere 20 kilometers wide can spin hundreds of times per second and remain intact. A timing shift of a microsecond, barely enough to click your tongue, can signal a planet orbiting a pulsar or a shift in the fog between stars. These numbers are absurd and yet ordinary in this domain. There are myths and confusions worth clearing up. Pulsars are not intentionally sending messages. The pulses are a byproduct of rotation and magnetic fields accelerating particles. We sometimes convert radio signals to audio to share the beat, but space is not making sound. Not every neutron star will ever be a visible pulsar from Earth. The beam is narrow. If it never sweeps across us, we never see it. Some pulsars are bright in radio. Some are quiet in radio but flash strongly in X-rays or gamma rays. The mix depends on how and where particles are accelerated. The lighthouse is real, but it is complicated and our vantage point matters. Astronomy with pulsars is a long game. You observe for hours to catch a tiny fraction of a second's pulse repeated many times. You observe for months to refine the period. You observe for years to watch spin down and to measure orbital changes. You correct for the motion of Earth around the Sun. You correct for Earth's spin and wobble. You correct for the exact position of the telescope. You correct for dispersion and scattering in the interstellar medium. You correct for clock drift in your own electronics. After subtracting every known dance step, you study what remains. That remainder is where new physics lives. Pulsars also carry personal stories of patience and craft. Jocelyn Bell Burnell's discovery was not luck dropped in a lap. It was attention to difference. It was the humility to ask why a small anomaly repeated at a sidereal rate. It was the willingness to check and recheck, to rule out the obvious, to hold back until the case was strong. That approach has guided pulsar science ever since. You build a case from timing you can trust. You chase surprises with models that can be tested. You share data so that signals can be checked across continents. Technology keeps widening the net. Low-frequency arrays map the sky for slow pulsars hiding behind heavy dispersion. Giant dishes with sensitive receivers pick up faint millisecond pulsars in the crowded plane of the Milky Way. Space telescopes catch pulsations from hot polar caps in X-rays and help measure radii by modeling how the brightness changes as the star spins. Digital processing makes it possible to search for acceleration. That trick lets us find pulsars in tight binaries where the frequency drift would have smeared out the signal. All of these gains feed the timing arrays and the gravity tests and the maps of the galaxy's plasma weather. There is delight in the weird systems found along the way. One pulsar hosts small rocky planets. Those worlds likely formed after the supernova from a disk of leftover debris. They circle a dead engine and still obey the old laws of gravity that govern every system. There are also pulsars that cannibalize their companions so efficiently that the companion might end as a tiny ember, perhaps even a diamond, like remnant rich in carbon. There are double neutron star systems that will merge in the distant future and spray heavy elements into space. When such mergers occur, they glow in light called a kilonova and ring the universe with gravitational waves. Gold and platinum on Earth were likely forged in such cosmic collisions. So the steady tick of today's pulsar may be the ancestor of tomorrow's jewelry. If you ask what remains unknown, the list is generous. We still debate the exact engine of radio emission. We model magnetospheres with computer codes that never quite capture the full complexity of a plasma driven by strong phi L's and rapid rotation. We argue over the equation of state of dense matter, which is a way of saying we seek the right recipe that links pressure to density inside the star. We try to understand why some pulsars switch modes of emission on timescales of minutes to months. We try to link glitches to microphysics and not just to metaphors. We push timing stability lower and lower. With more pulsars and timing arrays and more years of data, we hope to move from a hum of many black holes to a map where individual supermassive binaries stand out. We might even see a slow chirp from one pair getting closer over a decade. That would let us compare timing array results with future space-based gravitational wave detectors that probe higher frequencies. Together they would play a chord. Pulsars make a practical promise too. You could mount a small X-ray telescope on a deep space craft and, with a handful of bright pulsars, navigate reliably. Time differences are your ruler. The star map becomes a set of clocks. No ground station needs to send you commands. You are no longer tethered to two-way light travel times that grow longer with distance. Autonomy in the deep dark becomes real. Let's slow down and walk again through the birth scene because everything afterward depends on it. The massive star exhausts its core. Pressure collapses. At densities like an atomic nucleus, matter turns strange. Neutrons dominate. Neutrinos, ghostly particles, pour out and carry away energy. The core overshoots, rebounds, and sends a shock that the outer layers ride to freedom. The remnant is hot enough to glow in X-rays. The magnetic field is wound tight, sometimes twisted by the turbulence of collapse. The newborn neutron star can spin dozens of times per second. In the first years, it may power a bright nebula with its wind, as in the famous Crab Nebula. The beam switches on and the lighthouse begins its sweep. As time passes, the period lengthens. If the star finds a companion and steals matter, it can spin up and become a millisecond pulsar. If not, it may grow quiet as a radio source. It never stops being a neutron star. It simply fades from our particular ears. When you imagine the beam, do not think of a flashlight bulb. Think of a fan with structure. Near the surface, particle acceleration can light up small hot spots that pulse in X-rays. Higher in the magnetosphere, particles moving along curved field lines emit gamma rays. Somewhere in between, a complex dance of charge and current creates coherent radio emission. Each region contributes to the final pulse profile we record. Our line of sight slices through different parts depending on geometry. That is why one pulsar might show a single sharp peak while another shows two peaks or a broad shelf. The orchestra is one instrument, yet it plays many voices. The interstellar medium continues to play its own role. Dispersion we can correct by measuring the delay across frequency bands and subtracting it out. Scattering is trickier. Small, scale clumps in the plasma scatter radio waves and smear the pulse into a tail, like a candle seen through frosted glass. Scattering varies with time as the Earth and the pulsar move, and as the plasma itself evolves. Long monitoring lets us learn its habits. That knowledge is not busy work. It improves timing. It also tells us how energy flows through the galaxy's magnetic fields. Supernova remnants inflate bubbles. Stellar winds carve channels. The galaxy's disk hosts giant clouds and empty cavities. Pulsars, by crossing all these structures, write a logbook of the trip. Glitches deserve one more pass because they are the most direct signals from inside. The superfluid in the inner crust carries spin and quantized vortices. Those vortices can pin to the lattice of nuclei. As the star slows, the superfluid resists. Stress builds. Then a threshold is reached. Many vortices unpin and cascade outward. The crust suddenly spins a touch faster, dragged by the superfluid's stored angular momentum. The signature is a sudden jump in frequency followed by a slow relaxation. Some pulsars, like Vela, glitch often, almost like a heartbeat. Others glitch rarely. Modeling these events links astronomy to condensed matter physics and nuclear physics. It is a bridge across fields that do not usually share a lab. All this science rests on the quiet heroism of timing. You build a stable reference. You know exactly where Earth is in space at each moment, down to microseconds, using planetary ephemerides. You correct for Earth's motion so that all times are quoted as if you were at the solar system's center. You relate observatory clocks to international standards. You fold the data with the best estimate of the period and its derivative. You fit a timing model that includes position, proper motion, parallax, and, if needed, binary orbital elements. The residuals, the tiny differences between predicted and observed times, are the gold. They carry gravity's whisper, plasma's rustle, and the star's internal murmurs. In the end, you hold two truths at once. A pulsar is a relic of violence. A massive star died to make it. Yet a pulsar is also a source of order. It offers a beat that helps us weigh gravity, map plasma, and navigate space. The contrast is not contradiction. It is the universe's habit of turning endings into tools. Hold one last image. Far from Earth, a city-sized star turns with unthinkable steadiness. Its beam sweeps empty space again and again, like a lighthouse that has forgotten the storm that built it. The pulses cross dust and plasma and time. They tap the face of our instruments and make a pattern. On some quiet night, across 1,000 light years, a very slow ripple in space-time passes and stretches the path by less than the width of a human hair, and the tick arrives a sliver late. We notice. We add another mark to the ledger. We keep listening. And if you stand under a clear sky and imagine the galaxy as a dark sea, imagine too that scattered across that sea are lighthouses whose clocks never sleep, their beams swinging unseen through the night, and that somewhere, right now, one of them is writing a perfect second on the far shore. There's another way to feel what a pulsar really is. Imagine a bell cast from ultra-dense matter, so stiff it could stop a bullet's thought. Strike the bell once, and it keeps its note by turning. The note is timing. The mallet is gravity frozen into spin. The air around it is not air at all, but a storm of charged particles trapped to magnetic lines that loop and open like out strings on an invisible harp. Each rotation plucks those strings and sends a wave through space. We do not hear it with ears. We count it with radios and X-ray detectors, and the counting itself becomes knowledge. Close to the star, the magnetic field rules. Farther out, there is a boundary where the field lines can no longer keep up with the rotation. Astronomers call that distance the light cylinder, because a point rotating at that radius would need to move at light speed. Inside that cylinder, field lines close back on the star like hoops. Outside, they open into space. The open zones near the magnetic poles are launch pads. Particles accelerate along the open lines and radiate. The details are messy and alive. Currents thread the magnetosphere. Charges flow out and return. Tiny gaps appear where electric fields can grow strong and fling particles to extreme energies. The pulse you receive is the sum of all that structure, sliced by your line of sight. Sometimes the structure changes. A pulsar can spend hours in one personality and then switch within minutes to another. We call that mode changing. The pulse shape shifts. The timing may wander by a hair. In other cases, the pulsar goes quiet for a while. That's nulling. Nothing arrives, not because the star has stopped, but because the coherent radio engine has slipped for a time. Then it returns as if someone lifted a finger from a switch. These moods are clues. They say the magnetosphere is not a fixed sculpture. It breathes like a fire does when the wind changes. Look closely at a pulse, and you may see a staircase of subpulses drifting across the profile. That drift is not random. It looks like a pattern that slides with each rotation. One story for it is simple and beautiful. Imagine sparks that circle above the polar cap, not as fire, but as zones where particle acceleration is strongest. As those zones rotate within the magnetic footprint, our line of sight cuts a different slice each time. The drift is geometry written as timing. Whether that picture is the whole truth or just a part, the phenomenon reminds us that even a perfect clock can show art in its face. Now widen the view to the galaxy itself. Radio waves from pulsars arrive polarized, which means the electric field swings mostly along a preferred plane. As those waves cross the Milky Way's magnetic fields, the plane of polarization twists, a subtle effect called Faraday rotation. Measure the twist across frequencies and you get a number called the rotation measure. Put rotation measure next to dispersion measure and you begin to trace not just how many electrons lie along the path, but how they are threaded by magnetic fields. With many pulsars mapping many lines of sight, the galaxy's hidden magnetism takes on shape. You learn where fields reverse direction. You learn how tightly the spiral arms wrap their invisible wires. There is also twinkling, the interstellar version. Starlight twinkles because air jiggles in Earth's atmosphere. Pulsars twinkle because thin clouds of plasma drift between us and them. Those clouds act like shifting lenses that focus and defocus radio waves. The pulse can grow stronger and weaker over minutes or hours. Sometimes two paths around a cloud interfere, like ripples that meet in a pond. The pattern they make across frequency is a fingerprint. Read it well and you can estimate the size and motion of the lensing cloud. In rare cases, the lens acts almost like glass, magnifying the star for a short time. We call those episodes extreme scattering events. A pulsar does not mind. It simply keeps time while the glass slides by. Some pulses come with a bonus. After the main beat, there's another, fainter one nearly half a turn away. That is an interpulse, often the sweep of the beam from the opposite magnetic pole. When both poles are visible, you get two lighthouses for the price of one, each with its own character. If the star slowly wobbles, a motion called geodetic precession in a binary, your line of sight gradually moves across the beam. Over years, the profile evolves, then fades, then returns in a new costume. You are watching a lantern from different seats in a theater as the stage turns. Let's drop into the famous systems that taught us the most. The first great binary pulsar revealed orbital decay as predicted by general relativity. The orbit shrank by the amount you would expect if the system were leaking energy in gravitational waves. That one achievement turned timing into a test bench for gravity in regimes far from the solar system. Then came the double pulsar, where both stars are clocks. In that system, you can time how the pulses slow when one beam passes behind the other and must traverse curved spacetime. You can time how the angle of the orbit shifts with each year. You can see how one pulsar's wind affects the other's magnetosphere, turning the second's beam brighter and dimmer through the orbit. It is a laboratory that weighs almost the mass of two suns and yet fits within a space smaller than the Earth. Moon system. Planets around pulsars sound like a dare, yet they exist. The first well-confirmed worlds found outside our solar system circle a pulsar. They are small and rocky. They likely formed from a disk of debris after the supernova, a second generation built in a harsher nursery. We know they are there because timing saw them. The star wobbles as the planets tug it. The pulses arrive early and late by amounts you can measure in microseconds. No sunlight warms those worlds. Their sky is a cosmic clock face. Their seasons are the stable arc of mathematics. Millisecond pulsars dominate the timing arrays because they are nearly absurdly steady. To build an array, you gather dozens of them spread across the sky and watch them for years. Each pulsar is a point on a map. A very slow gravitational wave passing through will pull some points closer and push others away by microscopic amounts. The signature of that pull and push has a pattern. Pairs of pulsars separated by a small angle on the sky react in a way different from those far apart. Stack years of data. Cross-correlate the timing residuals. If the pattern matches the geometry predicted for a background of supermassive black hole binaries, you have heard the hum. It is a detection that takes patience rather than spectacle. There is no quick chirp. There is a slow lift and sag that only a ledger can reveal. As arrays mature, they move from hearing a general murmur to picking out soloists. A nearby pair of giant black holes, millions to billions of times the sun's mass, may rise above the background one day. Its signal would drift in phase across years. You might even see hints of its orbit shrinking as the system loses energy. Combined with data from future space-based detectors tuned to faster waves, the story would cover a long stretch of the binary's life. Gravity would be traced with lines that cross instruments and decades. Pulsar wind nebulae are the smoke rings of these engines. The wind from a young pulsar slams into the expanding debris of the supernova. Where they meet, a shock forms. Particles cross the shock and pick up extra energy. Magnetic fields twist and light up. The result is a glowing cloud that shines in X-rays and visible light with rings, wisps, and jets. The Crab Nebula is the archetype. Time-lapse images show waves moving outward like ripples in a fountain. The pulsar at the center twitches and the cloud responds. It is a machine and a dance written into gas and light. Magnetars deserve another careful glance because they live at the far edge of what magnetic fields can do. In a giant flare, a magnetar can release as much energy in a second as the sun does in many years. The pulse train that follows rings down like a bell struck hard. The star's surface oscillates. Those vibrations tell us about the crust's stiffness. Occasionally, magnetars show an anti-glitch, a sudden slow down instead of a speed, likely tied to magnetospheric torque changes. Again, the lesson is that the engine and its atmosphere are coupled. A change above can nudge the spin below. If you want a map of pulsars as a family, plot rotation period against the rate of change of that period. The points scatter into bands. The young, fast pulsars live up and to the left, where periods are short and slow down is strong. The old, spun-up millisecond pulsars live low and to the left, with tiny slowdowns. Between lies a graveyard where many neutron stars likely rotate, but do not beam in radio toward us. The borders are not sharp. They are trends. A star can cross them by changing its magnetosphere or by gaining spin from a companion. The plot is a biography written in 2 numbers, and it hints at the life cycle from explosive birth to recycled old age. What about the surface itself? It is not a smooth ball of metal. The crust is a crystal of nuclei packed together. The base of the crust likely hosts nuclear pasta, those rod and sheet phases that minimize energy in crowded conditions. The thickness of the crust and the stiffness of that pasta affect how the star rings after a quake. Deeper in, the superfluid may coexist with a superconducting sea of protons threaded by magnetic flux tubes. Those tubes can pin to neutron vortices. When the star spins down, the vortices must move. If they pin, stresses build. When they unpin, you get a glitch. The microphysics is busy and cold and utterly beyond direct touch. Pulsars are our only route in. X-ray timing adds another handle on the interior. Hot spots near the magnetic poles sweep into view as the star rotates. If you can measure the brightness rise and fall with enough precision and know the star's distance, you can fit models of light bending in strong gravity. Light from the far side of the star can curve around to you. That bending depends on the star's compactness, which is mass divided by radius. Fit the curves and you constrain the radius for a star of known mass. Do that for several stars and the equation of state, the recipe for dense matter, is boxed in from 2 sides. In tight binaries, the pulsar wind can blow a tail off the companion. The companion can swell and block the beam for a part of the orbit. Those eclipses are laboratories too. The eclipse shape tells you where the wind is densest. Changes in pulse arrival times during eclipse reveal how the electrons in that wind are stirring. The names Black Widow and Redback are vivid for a reason. These systems eat their companions over time. Some companions may dwindle to planet mass embers. Some may be ground into dust. Pulsars in globular clusters are a world of their own. Those clusters are ancient and crowded. Stars pass close. Binaries exchange partners. A neutron star can capture a new companion. It can be spun up again and again. That's why clusters brim with millisecond pulsars. Timing them lets you weigh the cluster's mass and even trace the slow drift of the cluster through the galaxy. The cluster itself is a clockwork of many small clocks. There is a small paradox about precision. The better the clock, the more sins elsewhere are revealed. To time a pulsar, you must know Earth's path around the Sun beautifully well. Planetary ephemerides are refined in part because pulsars demand it. The stations on Earth must keep clocks that do not wander. The corrections from observatory time to international time must be clean. Even the radio receivers must be calibrated so that they do not add spurious delays that mimic physics. Each improvement ripples forward. As the human part grows steadier, the cosmic part steps forward into focus. The human story loops back to patience and attention. A student stared at long paper charts and noticed a tiny regularity. Decades later, teams span continents and share terabytes of data to find a slow wave that takes years to crest. In both cases, the art is the same. Look long enough and care enough to tell signal from habit. There is pleasure in this that has nothing to do with glory. It is the pleasure of a pattern finally making sense. Sometimes a pulsar behaves not like a stable clock, but like a musical instrument being tuned. That is timing noise, a wander in the residuals that resists clean modeling. Young pulsars often show it. Whatever its cause, it reminds us that nature does not sign contracts for smoothness. The star is still a clock. It is just a clock set on a table that trembles. Long baselines average out some of this shake. For the rest, we learn new tricks, new filters, new ways to admit uncertainty without losing the thread. There is poetry in how tiny effects point to huge things. A shift in arrival time smaller than a blink tells you a companion star exists. A slow, common drift among many pulsars tells you that galaxies you will never visit host pairs of black holes heavy as millions of suns. A slight change in polarization angle tells you that the galaxy's magnetic field leans one way and not another. The scale mismatch is not a problem. It is the feature that lets us use one domain to read another. Consider where all this might go. Imagine a timing array with hundreds of millisecond pulsars, each measured to within tens of nanoseconds. Imagine tracking them for decades. The background of slow gravitational waves would come into focus. You could separate the sum into pieces. You could identify individual black hole pairs. You could catch a system on the brink of the faster band where a space-based detector will hear it sing. Cross those measurements and you have a story that stretches across frequencies and tells you how giant galaxies grow by eating one another's hearts. Imagine also a fleet of spacecraft that navigate by pulsars as naturally as birds navigate by the sun. A ship outward bound to Neptune listens to a handful of bright X-ray pulsars and knows its position without calling home. Another probes the space above the sun's poles and reads the sky's clocks to stay on course while radio contact is thin. Near a small icy moon, a lander keeps time against a distant beacon because its own clock would drift too fast in that cold and radiation. The sky holds the time. The craft trusts it. If you want a last comparison that makes your tongue rest on the right words, try this. A pulsar is a lighthouse and a clock and a seismograph and a weather vane and a depth sounder, all packed into a spinning bead of matter that could sit on your city map like a pinhead. It tells you where you are. It tells you how gravity behaves. It tells you how much fog lies between. It tells you when its own crust slips. It tells you when space itself stretches. Think of the night ahead. Somewhere in the dark, a newborn neutron star is switching on. Its beam is lighting a ring of gas that used to be a sun. Its period is young and quick. Its slowdown has only begun. Elsewhere, an old millisecond pulsar is coasting. It spins so cleanly that its pride is its steadiness. Far beyond, two supermassive black holes are circling each other in a galaxy we can only point to. The wave they make is too slow to see in a day or a year, but it crosses the paths to 1,000 clocks, and with time we will write the wave's shape in a ledger and call it discovery. And now, leave yourself with a single picture. In the mind's quiet, set a small shining city on the tip of a pin. Let it turn hundreds of times each second without a tremble. Let a beam sweep from poles that aren't aligned, and watch that beam, invisible to eyes, draw a fine white tick across the dark. Steady, honest, and so exact that when the galaxy breathes, you can feel it in the space between two beats. Good night.